This is the mini lesson for the ideal gas law. First, we're going to review the quantity of the mole. Now, mole is a chemical quantity that allows us to compare the different size worlds that we study. So a mole will let us quantify the number of particles. 1 mole is equal to 602 sextillion particles. So it's a conversion factor between the atomic world and the macro world that we exist in. Moles will also let you convert between uh, that quantity, so measurement of an amount of a substance, to a mass that you can measure on a balance in order to do an experiment, with the conversion factor that 1 mole equals the molar mass of that substance. Now we're going to use moles to convert between that and a volume of a gas at standard temperature and pressure. So 1 mole is equal to 22.4 liters of a gas at standard temperature and pressure. And we're going to be using this relationship with the ideal gas law. And this is the ideal gas law. When I was in college, me and my friends nicknamed it PivNert to try to remember it, so we didn't have to memorize just the letters. But basically, I'm going to go through variable by variable. Capital P is for pressure, and pressure is going to be how frequently do the gas particles collide with each other or the edges of the container. Capital V is volume, which represents how much space the gas will occupy. Lowercase n is moles, and it tells you how many moles of gas particles there are in your sample. R is the gas constant. It's a value that does not change and will be provided for you. And capital T is temperature, and it tells us how fast the gas particles are moving. It's a measure of their kinetic energy. So real gases will behave like an ideal gas under two situations. They need to be at a low pressure, so the particles will collide infrequently with each other and the edges of the container. And they need to be at a high temperature so that the particles are moving very quickly. Most real gases will behave similar to an ideal gas, and this allows us to make predictions about the behavior of gases using the ideal gas law. So these predictions, we're going to be using the ideal gas law, and this is going to be something you might remember from math. We're talking about inverse relationships versus direct relationships. And we'll always be comparing two variables at a time. And in order to have that comparison, all other variables in the equation have to remain constant. So the first one we're going to look at is pressure and volume. So number of moles and temperature will remain constant, and so does the gas constant. So when we look at pressure and volume, they have an inverse relationship, which means if pressure were to increase, volume would decrease. And then the other way, if volume were to increase, pressure would decrease. So they do the opposite of each other. And notice that they are on the same side of the equal sign. The other variables that have an inverse relationship are moles and temperature, lowercase n, capital T. They are also on the same side of the equal sign. And if number of moles were to increase, the temperature would decrease. And if number of moles were to decrease, the temperature would increase. They're going to do the exact opposite of each other. When we look at pressure and temperature, they're on opposite sides of the equal sign, and they have a direct relationship. So if pressure were to increase, temperature would also increase. Pressure and moles are also on opposite sides of the equal sign and have a direct relationship. So if I were to increase the pressure, it would increase the number of moles. Volume and moles, also on opposite sides of the equal sign and also have a direct relationship. So increasing volume will increase number of moles. Decreasing volume would decrease number of moles. They behave the same. And then finally, volume and temperature on opposite sides of the equal sign have a direct relationship, so that if volume was increased, temperature would also increase. So let's look at a couple of examples. And remember, we're always going to be looking at two variables at a time and have to assume that all the other conditions are kept constant. So for example 1, what would happen to the pressure of a gas if the temperature was increased? So we're looking at pressure and temperature, and they're on opposite sides of the equal sign. So this should be a clue that they are going to have a direct relationship. So if temperature were to decrease, as is said in the problem, pressure would also decrease. And this is because pressure and temperature have a direct relationship. Therefore, the pressure of the gas would decrease if the temperature was decreased. Example 2. What would happen to the volume of a gas if the number of moles of gas was increased? So we're looking at capital V, lowercase n, and it's telling us that lowercase n was increased. They're on opposite sides of the equal sign, so that should be a sign that they have a direct relationship. So therefore, volume would also increase because volume and moles have a direct relationship. And you would, in your explanation, say, therefore, the volume of gas would increase if the number of moles increased. For example 3, what would happen to the volume of a gas if the pressure was increased? So we're looking at capital V and capital P. Look at now, these are on the same side of the equal sign, and this was an indicator that these variables will have an indirect relationship. So if pressure was increased, then volume would do the opposite. Volume would be decreased. And that's because pressure and volume have an inverse or indirect relationship. I don't think it's indirect, I think it's inverse. My apologies. So the explanation would be the volume of gas would decrease if the pressure was increased because of this inverse relationship. Now, a real world connection is airbags. Airbags have become very prevalent in cars. There used to just be one in the steering wheel, but now they're all over, and they have increased the survival rate of people that are in car accidents because they create a softer surface in that collision, so there's less damage done to the human body. And the way it works is with this chemical reaction. You have a solid sodium nitride. When there is a collision, heat is triggered, and it causes a chemical reaction where the sodium nitride transforms into solid sodium and nitrogen gas. The nitrogen gas is what then inflates the airbag so that whenever you come forward instead of here in the steering wheel, you're going to hit what is a somewhat softer surface. Now, before the reaction, there's no gas. You only have the solid sodium nitride. The nitrogen gas is formed during the reaction. And the ideal gas law is used to predict how many moles of gas is needed for an effective airbag. You don't want to have too much because then you're going to be punching the person with the airbag. So it'd be like an extra collision in an already very violent situation of a car collision. But if you don't have enough, then they're going to end up hitting the hard surfaces within the car. So you have to use the ideal gas law in order to engineer an effective airbag. So the ideal gas law, we're looking at the number of moles and we're looking at volume. So these two variables is what we're interested in when it comes to airbags. So, as the number of moles of a nitrogen gas increases, so will the volume of the airbag, which is what we want. So, you can see how the ideal gas law is applied to this situation and is used to help make sure that people are safe in car collisions with these airbag safety systems that are incorporated. All right, so you have some practice problems you need to do, and make sure you fill everything in your notes and glue it into your notebook.